There are these quiet, almost invisible battles happening all around us, all the time. Slow, relentless chemical reactions that are constantly reshaping our world, from the car in your driveway to our most famous monuments. Today, we're going to pull back the curtain on the science of decay, a process you might know as corrosion.
And to really get our heads around it, let's start with a mystery that's literally hiding in plain sight. I mean, we all know the Statue of Liberty is green, right? But here's the kicker. She didn't start out that way. Not even close.
Okay, so check this out. When Lady Liberty showed up from France way back in 1886, she was this brilliant, shiny brown color, the actual color of copper. So how on earth did she get that iconic blue-green look we all recognize today?
Well, the answer is this really fascinating mix of chemistry, pollution, and just a lot of time. So let's break down exactly what happened to her copper skin, step by step. This definitely wasn't some overnight paint job. It was more like a slow dance with the elements over decades. First, the oxygen in the air started to turn the copper kind of reddish, then that deepened to black. But the real game changer, that came from the air in New York City at the time. All the sulfur from burning coal mixed with the rain, and that acid rain reacted with the dark surface to create that unique blue-green layer, the patina, that has defined her ever since. And here's the really crucial part. That green layer isn't a sign of weakness or decay. It's actually the opposite. It's a process called passivation. See, that patina formed a tough protective shield around the statue, sealing the copper underneath from all the wind and rain. It basically stopped any more corrosion in its tracks. In a way, the statue literally saved itself. But here's the twist. While this whole process was a happy accident for the Statue of Liberty, for the rest of the world, this exact same chemical force is a massive, and I mean incredibly expensive problem. Just look at that number for a second. In the United States alone, the cost of fighting corrosion every single year is over $500 billion. That is more than the entire economy of a lot of countries. And it's all because metal is just trying to return to how it exists in nature. So let's put an official name to it. Corrosion is just the breakdown of metals through a natural electrochemical process. It's nature's way of taking refined metals, like the iron in a bridge or the copper in a statue, and trying to turn them back into their more stable original forms, like the ores they came from. Okay, so this brings us to the main event, really. We've just seen a good kind of corrosion, the statue's protective patina. Now let's meet its evil twin. Yeah, the villain in this story, the one causing that $500 billion headache, is iron rust. It's the corrosion we're all familiar with, and believe me, it works in a completely different and way more destructive way. And this chart just nails the difference. The copper patina, our hero, goes through passivation. It makes a stable, tough shield that sticks right to the surface and stops corrosion cold. But iron rust, our villain, it's flaky, it's brittle. As it forms, it just breaks away, which constantly exposes fresh new iron underneath to more air and water, and that allows the destruction to just keep going and going until there's nothing left. The science behind this is actually really cool. When iron gets wet, these tiny little electrochemical zones pop up all over its surface. The best way to think of them is like millions of microscopic, self-destructing batteries. They're literally powered by oxygen and water, and they're the little engines that drive the reaction, turning solid iron into that flaky rust. So if rust is this relentless, destructive force, how in the world do we fight back? How do we protect all the vital iron and steel that our modern world is built on? Well, you give it armor. So how do we build this armor? It really boils down to three main strategies. You can think of it as a simple barrier, a change of identity, and a clever sacrifice. Let's look at painting, alloying, and coating. Painting is the most straightforward solution, right? It's just a physical shield. The paint keeps the water and oxygen away from the metal. Simple. But, and this is a big but, it's only as good as its coverage. The second you get a chip or a scratch, you've basically just sent rust an invitation to the party. A much more clever method is alloying. This is how we get stainless steel. By mixing in just a little bit of another metal, chromium, you basically give the iron a superpower. The chromium creates its own super thin, invisible, self-healing layer that protects the iron underneath. It's basically giving iron its own personal passivation shield, just like the Statue of Liberty's. And then there's coating, which you might know as galvanization. This is where we cover our iron or steel with a layer of a different metal, usually zinc. Now, zinc is more reactive than iron. So, yeah, it provides a physical barrier, but it's also doing something else, something incredibly smart. And that really clever trick is based on a fascinating idea called the sacrificial anode. Now, this idea sounds completely backwards at first. You're going to protect your important piece of metal by attaching it to another piece of metal that you want to corrode? You are literally offering up one piece of metal as a sacrifice to save another. So how does this actually work? Well, imagine you have a big steel tank buried underground for, say, gasoline. To protect it, you bury a block of zinc nearby and connect them with a wire. Because zinc is more reactive, it becomes the anode, the part of that tiny battery that corrodes. This forces the steel tank to become the cathode, which means it receives electrons and stays protected. The zinc block slowly gets eaten away over time, sacrificing itself to keep that important tank perfectly safe. So, from the color of a beloved monument to the invisible shield protecting our critical infrastructure, corrosion is this incredibly powerful force. It kind of makes you wonder, doesn't it? What other silent, invisible chemical battles are constantly shaping the world we see every single day?